In this video, I want to comment on different styles of free body diagrams. Consider the following situation. We have a 100-kilogram block on a frictionless inclined plane that's inclined at an angle of 30 degrees above the horizontal and is being pushed horizontally by some agent. And we assume that all of this is happening on the Earth. Now, I'll actually solve this problem in another video. My objective here is just to discuss different kinds of free body diagrams. The first comment I want to make is that this is not a free body diagram. This we can consider a representation of the problem, a sort of schematic, but it is not a free body diagram, as we will soon see. So let's shrink this and get it up and out of the way. Now let's consider a couple of different ways of drawing the free body diagram. In the free body diagram on the left, we represent the object, the 100-kilogram block, as a point, and we show the forces acting on that point that come from the physical parameters of our problem. So we have this 200 Newton force to the right. We've got the gravitational pull of the Earth on the object pulling down, and we have the normal force exerted by the inclined plane on the block pointing out here perpendicular to the inclined plane. We make every attempt that we can to try to draw these things in proportion. For example, if this is a 100-kilogram block, so the gravitational force acting on that block should be 980 newtons. So this arrow should be considerably longer than this one, about 5 times longer. Likewise, you try to draw this in proportion to the other forces on the problem. Sometimes you won't know those until you solve the problem, but you try to make every attempt to do that. Another common style of free body diagram is not to represent the object as a point, but to actually try to show the object itself as some sort of sketch and in the same orientation as the original object in the problem. So this is on an inclined plane. I try to show that incline action right here. But it still has all the same information. I've got this 200 Newton force pushing to the right. I technically could have also put it over here, but in these diagrams we often try to show the forces acting where they are. Boom, pushing to the right, force of gravity pulling down, the normal force pushing outward of the inclined plane pushing on the block. That's going to be outward here, perpendicular to the inclined plane. Now, I could have actually written the normal force differently. I could have shown that as an arrow right here, drawn that here, pushing up. It contains the same information. As long as you have the appropriate orientation and relative magnitude, size, and direction, and all that stuff for all your vectors, that's what you need. Now, it's important to emphasize some things that all correct free body diagrams have in common. You know, there are these different styles, but these are aids to applying Newton's second law. Newton's second law says that the sum of the forces acting on some object equals the mass times acceleration of that object. Consequently, the free body diagram shows only forces acting on the object. This 100-kilogram object represented here or here, these forces are acting on that object. These are not forces that the object exerts on something else. These are forces acting on that object. That is very important. Note also that we don't attach anything to the object other than the forces acting on that object. I may indicate somewhere to the side an acceleration if I'm confident the direction of the acceleration might be down the inclined plane or up the inclined plane. It might be hard to know before you solve this problem, but if I knew, I might indicate that in there. But I wouldn't put it on the object. I would show it off to the side so I don't confuse accelerations with forces. That's because the job of the free body diagram is to help you relate the forces in the problem to the acceleration of the object, but the forces are not the acceleration. Similarly, you wouldn't put other things attached to the object like velocities or positions or anything like that. These diagrams show only the forces acting on the object. Finally, you'll normally want to include a coordinate system with your free body diagram, the coordinate system you'll use for applying Newton's second law. And then once you have a coordinate system, you may then break some of these forces into components along that coordinate system. But I won't show that here.